So this is the first in a series of screencasts on geometric group theory, but it's a sequel to the series of screencasts on hyperbolic geometry. I'll start with just defining a notion of negative curvature, which applies for metric spaces. We give more than one definition, but for the first definition I have to restrict the class of metric spaces. Okay. So to do that, let's first look at a metric space. XD is a metric space, and throughout I'll assume that it's complete. Okay. Every metric space I consider will be complete, certainly not compact in general. Okay. You can assume separable if you're without any serious loss of generality. Okay. But first we look at geodesics in this metric space. So a geodesic, gamma mapping 0, 1 to x, is a map, which means a continuous function such that the length of gamma is the distance between gamma of 0 and gamma of 1. Okay. More accurate way to say this is a map from 0, 1 to x is a geodesic if its length is the distance between gamma of 0 and gamma of 1. Well, what do I mean by length here? This is what is in analysis often called the bounded total variation. So length of gamma, what we do is we look at 0, 1 and subdivide it. So I'm looking at points t1, t2, etc. And this is going to be tm, this is going to be t0. Okay, and then for such a partition I look at the sum I equals 1 to n of the distance between gamma of ti and the previous point, gamma of ti minus 1, and I take the supremum over all 0 being equal to t0, which is less than t1, etc., which is less than tn, which is 1. Okay, you could do this for any interval. So what this is saying is that you partition it and look at the distance between successive pairs of points, add this up and take the supremum over all partitions. This may be infinite, of course. Okay, so the above equation says that the length is finite and equal to the distance. Okay, unless of course we have spaces where we allow distances to be infinity, in which case we interpret it